Now what will be mx? Mx is the bending moment at a distance x at a section at a distance x. Mx will be equal to WL by 2 into x, because it's a positive thing, so plus sign, and this uniformly distributed load will give its net resultant at this point, and suppose this is Wx into this, that is x by 2. So essentially what we'll have is some sort of an anti-clockwise moment at this section. So this will be negative, Wx square by 2, right? Now this is equal to minus EI y double dash, right? Because it's a case of a sagging moment, what we have is, if this is positive, the slope is decreasing obviously, so it will be negative. So this is what we have. Now we can write this in the form of EI y double dash, right, plus WL by 2 into x minus Wx square by 2 is equal to 0. Now this represents essentially a differential equation, and what I do is I divide all the three terms by EI. So essentially I rub this out and write here EI, and this is also 2EI. Now if I multiply all these factors by dx and integrate it, then we essentially what we get is, or y dash will be equal to WL by 2 EI into x square by 2 minus W by 2 EI x cube by 3 plus C1, right? But C1 is the constant of the integration, right? Now what are the boundary conditions here? Here it's a case of a deflected pattern will be like this, right? So obviously at this point there will be x is equal to 0, y then will be equal to 0, right? There will be some sort of a y dash or a slope at this point. At this point essentially you will have the maximum value at L by 2. You will, at x is equal to L by 2, I am having the maximum value, but here what will happen is that the bending moment essentially goes from some sort of an increasing function to some sort of a decreasing function, right? So essentially this will be the point wherein maximum bending moment will occur, and essentially at the point of maximum bending moment we know that the slope is 0. That is, the slope of the bending moment diagram is 0, or the shear force is equal to 0. So we can write this as, at this point we can say that dy dx will be equal to 0, right? So what next? The next thing that we got to do is we got to utilize this boundary condition, that is x is equal to L by 2 dy dx is equal to 0, and we can find the value of C1 from this. This, if it is 0, we can write this C1 as WL by 4 EI into x square by 2, that is L square by 4, plus, oh this, I'm sorry, this will be minus and this will be plus, this will be W by 6 EI into L cube by 8, that is equal to, this is 16, this is 48, and one can do it pretty easily. So this is a 48 EI, this is 16, so minus 3 WL cube plus 1, that is equal to WL cube. So this will be equal to minus WL cube by 24 EI, right? And I can substitute this in place of C1, so I can rub this out and I can write this as minus WL cube by 24 EI is equal to 0. So this is a general equation that we have for slope, and let us write this in a fresh space. So what we have is, number one, what we have is y dash is equal to WL cube by 24 EI, WL cube by 24 EI plus Wx cube by 6 EI, Wx cube by 6 EI. This is minus WLx squared by 4 EI, minus WLx squared by 4 EI. So this is equal to 0. Right, sorry, what am I writing? Right. The next thing that we're going to do is we are going to find out the deflection, and find the deflection again we got to multiply it with dx and integrate it again, and then what we'll have is y is equal to WL cube by 24 I should say EI into x plus W by 6 EI into x is 4 by 4 plus minus WL x is cube by 12 EI plus C2. Now putting y is equal to 0, x is equal to 0, that is at this point essentially C2 will be equal to 0. So this is my equation for the deflection, right? So what is y? At x is equal to L by 2 we get the maximum deflection. We have seen this from the deflected pattern, from the shape of the deflected pattern. So essentially at x is equal to L by 2, if we put it, it will be equal to, y will be equal to WL cube by 24 EI into L by 2, right, plus W by 24 EI into L to the power 4 by 16, right, minus WL by 12 EI L cube by 8, right. So I can write this as 24 into 16 means I think 24 into 384, and this 96, and this is 48. So I can write this as 384, and this will be 48, that is divided by 384 divided by 48 becomes 8. So 8, this will be 48, this will be 24 into 16, that is plus 1, and this will be 12 into 8, 96 minus 4 into WL to the power 4, or 5 by 384 WL to the power 4 by EI. So the deflection y will be equal to 5 by 384, which is a constant term, to WL to the power 4 by EI. And the slope at this point A will be essentially equal to, if I put x is equal to 0 at this point, then I get the slope, and that will be equal to y dash at essentially A. If this is suppose A, it will be equal to WL cube by 24 EI XX, so cancel out, so this will be my slope, and the slope, and this will be in this direction, that is in the clockwise direction, right. So this is my deflection, this is my slope. And by solving this differential equation, what I have achieved is, I have found out what is my slope and what is my deflection by a set of boundary condition that we can impose. Now the next thing that we need to know is, we know that m by